All right, hi guys, this lesson is on section 3.3, increasing and decreasing functions, as well as the first derivative test. So here first is our old definition, our pre-calc definition of what it means for a function to be increasing or decreasing, right? A function is said to be increasing on an interval if as x is getting larger, the y values are also getting larger. And a function is said to be decreasing on an interval if as x is getting larger, the y values are getting smaller. We could also say that a function is constant, so neither increasing or decreasing on an interval if as x is getting larger, the y values are staying the same. And we're familiar with that definition from our previous class. Okay, so since we have studied derivatives, we can use them to help us determine where a function is increasing or decreasing and come up with a more methodical process of determining these intervals for a given function. But before we can get to that process, let's kind of do this exploration where we're reading this graph that I've given you, and let's determine the open intervals where the function is increasing, decreasing, and constant. So you can pause the video right now and try that, and then we can compare answers in a second. Okay, so this function, reading the graph, looks like it is increasing. So the intervals where it looks like as x is getting larger, the y values are also getting larger, would be from negative infinity to 1. Also from 3 to 5, and then from 12 to infinity. So stating those intervals, here I'll use the same color, so negative infinity to 1, 3 to 5, and then 12 to infinity. Okay, and then for where, and that those intervals, or I'll save that in a second. Okay, so and then for where f is decreasing, I would say from 1 to 3 and 5 to 9. Yeah, it looks like just those two intervals. So from 1 to 3 and 5 to 9. Okay, and then last question, for where it looks like f is constant would be from 9 to 12. Okay. So what do we notice about the values of the derivative f prime at each of the on each of the intervals that we stated above? So this is another chance you could pause the video and see if you can make a statement about f prime for where f is increasing, where f is decreasing, and where f is constant. Okay, so for where f is increasing, you hopefully see that if you were to draw a tangent line to any point on any of those intervals, the tangent line would be positive sloping. Like the slope of the tangent line would be positive, meaning f prime would be greater than 0 on that interval. And then for where f would be decreasing, so looking at those intervals, if you were to think about drawing a tangent line to any point on any of those intervals, the slope of the tangent line would be negative, right? So we could say that f prime would be less than 0 on those intervals. And for where f would be constant, well, those would be horizontal tangent lines, so f prime would be equal to 0. Okay, and then for what do you notice about the derivative f prime at the endpoints of these intervals? Well, if we check it out, looking at this first point where the graph of f changes from increasing to decreasing, that point doesn't look like it's differentiable. So we would actually, it's a sharp corner, so we would have to say that f prime is undefined. Okay, same thing at x equals to 3, where the graph changes from decreasing to increasing, f prime is also undefined. Okay, at 5, it looks like there would be a horizontal tangent line there. The function would be differentiable, and f prime would be equal to 0. Okay, for where the graph changes from decreasing to constant, that's a sharp corner, so f prime would be undefined. And then same thing here where the graph changes from constant to increasing. So those endpoints, it looks like f prime is either undefined at the endpoint of each of those intervals or equal to 0. And that should sound familiar. So f prime is undefined or f prime equals to 0. So that means the x values at each of those points we would refer to as critical numbers or critical values. So the x values are critical numbers, right? Values that would make the derivative undefined or equal to 0. Okay. So based on this exploration, we can see that the derivative of a function would be greater than 0 whenever the function is increasing. It would be the derivative would be less than 0 whenever the function is decreasing, or the derivative would be equal to 0 when the function is constant. And we are allowed to say increasing on the closed interval as long as the function is continuous on the closed interval. And decreasing on the closed interval or constant on the closed interval as long as the function is continuous on the closed interval. You don't have to determine the derivative at those endpoints because the derivative could technically be undefined, like there could be a vertical tangent line at an endpoint, but the function would still be continuous continuous and increasing on the closed interval because f prime would be greater than 0 on the open interval. So notice that up here I explicitly asked for open intervals, and you just want to be careful and make sure you're reading questions closely. So if a question explicitly asks for open intervals, then answer with open intervals. But if it doesn't and you're being asked about like where a function is increasing or decreasing, if I hadn't specified open interval, then I would have included the endpoints, like on the interval from 3 to 5 for where the function was increasing. I would have included 1 from negative infinity up to 1. But you just want to make sure that you are reading questions closely. But how do we determine these intervals? So kind of taking all of our observations, the fact that at each endpoint where an interval changed from increasing to decreasing or decreasing to increasing, the derivative was either undefined or equal to 0. So there was a critical number at the endpoint of each of the intervals. So for determining in a more methodical way where a function is increasing or decreasing, besides just reading the graph, we could identify critical numbers on the domain or on the given interval that the function's defined. And then we're looking for a sign change in the derivative. So if the derivative changes from positive to negative or negative to positive, or I'm sorry, I'm getting ahead of myself. Sorry, we're just looking at what we're talking about for increasing or decreasing. So we're looking for where f prime would be greater than 0 or where f prime would be less than 0 in order to determine those intervals. So like for this first question about determining the open intervals where g is increasing or decreasing, and we're also going to justify here. Oh, wrong pen. Okay, we need g prime so that we can find the critical numbers, and g prime would be negative 3x squared plus 3. G prime is a polynomial, so we're just looking for where g prime would be equal to 0 in order to identify the critical numbers. We can think about factoring out negative 3. So x minus 1, x plus 1 for what that factors to. So x equals to 1 and negative 1 would be our critical numbers. Right, that's where g prime would be equal to 0. So we're going to take those critical numbers and put them onto an analysis line for g prime. Okay, so put the values in order, the critical numbers in order. Okay, and then thinking about using test values Like we could use -2, 0, 2, and plugging those test values into the derivative. Now I know that G prime is a parabola that opens down. I know -1 and 1 are the x-intercepts. Those critical numbers correspond to the x-intercepts of G prime. So I know the graph will go from negative to positive to negative. You are allowed to just think about plugging those values into G prime. And that's why I've labeled the analysis line as G prime. That's where I'm plugging in test values. So this tells me that the graph of G will go from decreasing to increasing to decreasing, right? Based on where G prime is negative, positive, negative, okay? And based on our knowledge of the graph of G of X, if we were to connect and kind of make that into a curve, that has the right end behavior, and that does look like a cubic, right? So the graph would look something kind of like that. Now here's the thing, our analysis line is not enough justification. It's not justification for where G is increasing or decreasing. And your analysis line will never be graded. You have to interpret the analysis line. So we can say that G is increasing on the interval from -1 to 1. And I'm using open interval because the question asked. If I weren't being asked for an open interval, based on my knowledge of G being a polynomial function, I would include -1 and 1. But because the question is asking for the open interval, that's why I'm answering as an open interval. So G is increasing on the interval from -1 to 1 because G prime is greater than 0 on this interval. We want to be specific. It's not positive everywhere, it's just positive on that interval. And then we can say G is decreasing on -infinity to -1, and don't use unions or intersections. Intersection would be incorrect here because that would actually be an empty set. But it's decreasing on the interval from -infinity to -1 and the interval from 1 to infinity because G prime is less than 0 on these intervals. Okay. And then next question, also asking about where this polynomial is increasing or decreasing. So we go to find h prime and get 3x squared. And then if we think about setting that equal to 0, well, the only solution would be x equals to 0. So that's our only critical number based on where h prime would be equal to 0. So if we put that value on the analysis line for h prime, notice though that if we use test values, h prime is positive to the left and right. So that means h is increasing to the left and right. We are familiar with the graph of x cubed minus 2, right? That's the chair function shifted down 2 units. And so it makes sense that there would be the horizontal tangent line at x equals to 0. Sorry, that's a funky looking graph. So what do we say for where h is increasing? Can we just say everywhere? Can we say from -infinity to 0 and exclude 0? This is kind of a weird question. So that's where, because it isn't super clear based on the analysis line, which is just side work, we can fall back to our pre-calc definition of increasing, which says if as x is getting larger, the y values are also getting larger, then the function's increasing. So if we think about values directly to the left of x equals to 0, the y values that correspond to those points would be smaller than the y value at x equals to 0. And if we think about points directly to the right, the y values would be larger than the y value at 0. So yes, h is increasing everywhere from -infinity to positive infinity. okay? And we could say that's like because h prime is greater than or equal to 0 on that interval. But this is referencing our pre-calc definition. Of increasing. And then to completely answer the question, h is decreasing nowhere. Now, when a function is increasing everywhere or decreasing everywhere over its domain or the domain given, we say that it's a monotonic function. Okay, so if the function is increasing over an interval from a to b or decreasing, then the function is monotonic. Okay, and that term will come up again later on when we talk about inverses. So we have discussed relative extrema in section 3.1 and how if relative extrema are going to occur, remember relative extrema are the same as local extrema, they'll occur at a function's critical numbers, but we didn't get any further than that. We ended up talking about identifying absolute extrema when extreme value theorem applied. So the first derivative test is actually going to be what we call our method for identifying relative extrema, and it's basically the same thing that we were just doing when we were trying to determine where a function was increasing or decreasing. So we're going to do the analysis line. We'll consider where the function is increasing or decreasing, but what we're really looking for is a sign change in the derivative. So if the function changes from increasing to decreasing, that's going to create a local maximum or relative maximum. If the function changes from decreasing to increasing, that's going to create a relative minimum. So we're looking for a sign change, and we're doing a similar analysis with the analysis line that we did in the previous problems when we were just thinking about increasing and decreasing. Okay, so for this next question, we want to find the relative extrema. Notice an interval is stated on the interval from 0 to 2 pi. We need dy over dx to find the critical numbers. So that would be minus sine of x. Thinking about setting dy over dx equal to 0. So sine of x equals to 1/2. On the interval from 0 to 2 pi, our solutions would be pi over 6 and 5 pi over 6. Okay, these are our critical numbers. All right, where dy over dx was equal to 0. So creating the analysis line, I am going to put 0 and 2 pi at the end, and then put my critical numbers of pi over 6, 5 pi over 6, and this analysis line is for dy over dx. That's where I'm thinking about plugging in test values. So choosing test values, so a value between 0 and pi over 6, I'm going to go with pi over 12. Even though that's not a unit circle angle, I know it is between 0 and pi over 6. And then I can use pi over 2, 3 pi over 2. Now, sine of pi over 12 would be smaller than 1/2 because sine of pi over 6 is 1/2. And if you're thinking about the unit circles, the y values would be smaller. So dy over dx would be positive, and then 1/2 minus 1 would be negative, and then 1/2 minus -1 would be positive. So the graph will go from increasing to decreasing to increasing on that interval. So we could answer questions about increasing and decreasing, but the question is actually asking us to find relative extrema. And we're going to justify as well for good practice, okay? So we have to interpret the analysis line because that's not graded. That's not justification. So we can say, looking at pi over 6, the graph changes from increasing to decreasing. I like to draw those arrows because I can see that there's a relative maximum occurs at that critical number. So I would say that a relative max, this function has a relative max or maximum at x equals to pi over 6 because dy over dx changes, you want to be really specific, from positive to negative at x equals to pi over 6. Okay, and then at 5 pi over 6, there's a relative minimum. Okay, so relative minimum at x equals to 5 pi over 6 because dy over dx changes, you want to describe the sign change, so changes from negative to positive. At x equals to 5 pi over 6. Okay, so those, we identified our relative extrema, and then we also did justification. Same process of first derivative test. So this whole thing, this was the first derivative test, FDT. So here's my incentive for having watched this video. If you pause this, or actually even if you watched it, you can get a point of extra credit on the 3.1 through 3.4 quiz, which will be after break, if you email me before we get back from break, so before your class happens after break on that Monday, if you email me a video of you teaching someone else how to do this problem, so explaining this problem to someone else, so finding the relative extrema using the first derivative test for this function. And if you don't, so you can explain it to a friend, somebody else in the class. You have to video yourself. I have to be able to see them. If you don't have somebody, or you're just not comfortable talking to someone, then, I don't know, teach your dog, or teach your cat, or a stuffed animal, or, I don't know, your imaginary friend. But I think it would be best, I think it would be impressive if you did a real person, especially if it would be really helpful if it's somebody in the class. I think you guys would benefit from that. But I'll give you a point of extra credit on the next quiz if you submit that, just for this problem. Okay? But let's get to it together. So we need critical numbers, so that means we need f prime. So thinking chain rule, derivative of the outside, leave the inside alone, times the derivative of the inside. So this ends up being 4x over 3 times x squared minus 1 to the 1/3 power. So for critical numbers, we do need to consider where the derivative would be 0 and where it would be undefined. So you could even just by inspection figure that out. So where a numerator would be equal to 0, 0. And then, right, this is for where f prime is 0 or undefined. And you don't have to write this part down. I'm just communicating that to you. Okay, and then for where f prime would be undefined would be -1 and 1. But you do want to check, are all of those values in the domain of f? Yes, they are, right? Because 0 to the 2/3 power would just be 0. So all 3 of those are critical numbers. So we can set up our analysis line for f prime, putting those values in order. And then we're thinking about plugging test values into f prime. Okay, and after plugging test values, it goes f prime is negative, and then it goes positive, negative, positive. The sign change, though, we've seen that. It doesn't always happen, so it's not guaranteed. You have to actually think about testing. And this is going into F prime, okay? So then now I'm ready to do the analysis. So it looks like, let's think about relative min first. So it actually looks like there's a relative min at 2 locations. So we can say there's a relative, F has a relative min, has relative minimums. At x equals to -1 and x equals to 1. Because F prime changes from negative to positive at these values. Oops. Or at x equals to -1 and 1. Okay. And then it looks like F has a relative maximum at x equals to 0 because F prime, and to get the extra credit, you have to justify, in case I didn't say it before. F prime changes from positive to negative at x equals to 0. Okay. And this last one, if you want, you can pause it and try this one on your own. I'm going to state first, x can't be equal to 0, just in case that ends up as being a potential critical number. We need to use, I'm going to use quotient rule here. So low d high minus high d low all over low low. Okay, so for what that would simplify to, if we distribute the 2x, what that would be 4x to the 5th minus 2x to the 5th minus 2x. Okay. And so that would be 2x to the 5th, which we could actually factor out an x, huh? So that would actually be 2x to the 4th minus 2 over x cubed. And we are allowed, we could factor out the 2, and then that would actually be x squared minus 1, x squared plus 1. Difference of 2 squares. Okay, so 1 negative 1 would make dy over dx 0. And 0 would make the dy over dx undefined, but 0 is not in the domain. So our only critical numbers are x equals to 1 and negative 1. Okay, we are not counting 0 because 0 is not in the domain. However, if we think about what happens at 0, there's a vertical asymptote. So could the function change from increasing to decreasing at a vertical asymptote, or decreasing to increasing? Yeah. And like, we want to take that into account. It couldn't be the location of relative max or min, but my suggestion is when you do make your analysis line, put 0 on it and label it. It's a vertical asymptote, right? And then we have negative 1 and 1 as our critical numbers. This is for dy over dx. So now I can think about test values. So -2, -1/2, 1/2, 2. So it goes negative, positive, negative, positive. So decreasing to increasing, decreasing to increasing. But even though the graph changes from increasing to decreasing at 0, it can't be a relative maximum because that's a vertical asymptote. The graph isn't continuous there. There is a non-removable discontinuity. So there's actually 2 relative minimums. So there's relative minimums at x equals to -1 and x equals to 1 because dy over dx changes from, can't write right now, negative to positive at these values, or at x equals to -1 and x equals to 1. Okay, so that's first derivative test, doing the analysis line and interpreting the analysis line to determine where there are relative or local max or mins.